Take a look at this electric vehicle, stranded in the freezing snow. Extreme winter temperatures expose a major vulnerability of modern EVs, causing batteries to lose their stored range or fail to charge. Beyond the cold, these vehicles face an economic risk. During the 2022 supply chain crisis, the price of lithium spiked by nearly 800%, highlighting the danger of building global transportation around a single volatile metal. The proposed solution is the sodium-ion battery. This chemistry uses sodium as the primary charge carrier instead of lithium. Sodium is the sixth most abundant element on Earth, making it essentially as common as table salt. Major automakers are placing massive bets on this alternative. Industry giants like BYD, Northvolt, and CATL are currently building enormous, dedicated gigafactories to mass-produce these specific cells. However, there is a paradox in the current market. Despite utilizing an almost infinitely abundant raw material, mass-produced sodium-ion cells currently cost about the same as budget LFP batteries. LFP, or lithium iron phosphate, is the standard low-cost lithium chemistry used in many entry-level EVs. If the foundational raw material is universally available, the resulting physical battery should be much cheaper to manufacture. The reason it remains expensive comes down to the physics of the atom. Lithium and sodium sit close to each other on the periodic table, but they exhibit a significant physical difference at the microscopic level. This diagram shows a scale comparison of the two charge carriers. A standard lithium ion has a mole volume of 21.3 angstroms. An angstrom is a tiny unit of length used to measure atoms. The sodium ion on the right is much larger, measuring 39.3 angstroms. Expanding this view to two identical battery containers, we see the result of that size difference. The container on the left holds significantly more lithium ions than the sodium container on the right. This illustrates volumetric energy density, which measures how much electrical energy fits in a specific space. Because sodium ions are larger, they take up more physical room to store the same amount of charge. To match a lithium battery's range, a sodium battery has to physically scale up. As the diagram shows, it requires extra internal layers, more separator material, and a specialized anode structure made of hard carbon, a material that requires high temperatures to process. This physical reality offsets the low cost of the raw salt. The sheer volume of extra physical packaging and the specialized carbon required to house those larger ions consumes the potential savings. To make these batteries viable, engineers focused on cutting costs in other components. In a traditional lithium cell, manufacturers must use expensive copper foil for the anode's current collector. They use copper because lithium destroys cheaper aluminum at low voltages. Sodium has a distinct chemical advantage. It does not react with aluminum in the same way. Engineers are now swapping out that dense, expensive copper for lightweight aluminum on both sides of the cell. This change slashes collector costs by 70% and reduces the overall weight of the battery. Sodium also handles the freezing temperatures that stall other EVs. This simulation shows what happens to standard lithium batteries at -40 degrees Celsius. The liquid electrolyte thickens, trapping the ions and halting the chemical movement needed for power. Sodium ions form weaker chemical bonds with the electrolyte. This allows them to move through the thickened liquid more easily, retaining over 90% of their capacity even at -40 degrees. By utilizing the aluminum loophole and this temperature resilience, engineers found a specific niche for sodium. It provides reliable performance in extreme conditions where lithium batteries often struggle to operate. This technology is now reaching the market. This is the Chang'an Nivo A06, one of the first mass-produced passenger vehicles equipped with sodium-ion technology. This vehicle uses CATL's Naxtra architecture, providing a range of roughly 250 miles, while remaining functional in extreme cold. Rather than choosing one chemistry, automakers are deploying both elements within a single vehicle. This 3D visualization shows a dual chemistry pack. It contains an interleaved grid of both high-density lithium-ion and cold-resistant sodium-ion cells. They are managed together by a battery management system, or BMS, which is the computer that controls how the vehicle draws power. The BMS arbitrates between the two chemistries based on the environment. On a standard highway trip, the car uses the lithium cells for range. But as the temperature drops below freezing, the system switches the draw to the sodium cells to ensure stable power and reliable starts. Sodium ion acts as a strategic hedge against material shortages, while providing the thermal resilience needed for electric vehicles to succeed in the world's coldest climates.